Hello, class. This will be the recorded lecture. We're going to chapter 12. Kind of skip around a little bit now. So in my opinion, we've finished what I would consider the basic statistics part of the class. And the next few things are going to be a little more specific and not harder, but I would consider a little more advanced when you talk about analysis. And what we're going to do and why I wanted to make sure we got to chapter 12 is to talk about some qualitative data. As an engineer, I don't usually deal with qualitative data, but I do know that we have quite a few other different majors in the class that I teach here. So I think it's important to deal with the qualitative data. And so there are three different types of tests that we were going to do. And the first one is called the goodness fit test. And so basically, these tests are predicated on this chi-square distribution that I mentioned previously. So what we're going to do is just kind of review that distribution and then walk through the goodness fit test. And so here, what we're calling again, finding these critical values. And so just like when we were calculating z-scores and t-scores, or t-values and z-values, we're going to calculate chi-square values. And they're, again, predicated off the fact of this table. And again, just to review what the chi-square distribution looks like, it's what we call skewed to the right, which implies that the peak is to the left. And as the degrees of freedom get larger, you'll find that it looks more and more and more like a more flatter, more normalish looking distribution. But most of the time when we do these calculations, you'll see that our degrees of freedom, which is the same calculation as we did on the t-scores, is the total samples minus one. And you'll see these values can get pretty large. So again, just to review how to read the chi-square table. And so the way to do that is you're going to get a critical or a significance level alpha again. And the alpha is dependent on the column that you're going to read in the table. And then the degrees of freedom is the other part, and you kind of match the two, and out comes a number. What's a little weird about this table compared to, say, the z-score and t-score table is that it's a right tail one. So you could see that the 0.05 in this case is 5% to the right. And so you would see that this would be kind of all the way up if you ended up with the bigger values. And so the table that I uploaded to our Canvas site is set up exactly the same way. And so I will be referring to this table, but say like we had a degrees of freedom of 12, and we go over to 0.05 or 5% for the alpha, you could see our chi-square number is 21.026. So when we do this, we're going to be comparing this chi-squared with a new test statistic that we're actually going to calculate. Another thing about a chi-squared that I don't think I mentioned, but it is important, is the chi-squared numbers are always positive. Where when we were doing t-scores and z-scores, we had negative and positive numbers for that. Here, the chi-squared numbers are always positive. Okay, so let's take a look at doing a goodness fit test. And what I will do is three different ways. One by hand, show you how to calculate the test statistic by hand, show you how to use the spreadsheet, which is really easy, and also introduce to you how to use your calculator, which is super similar to the spreadsheet. But you really need to understand at least two of the three ways. You need one, technology. So pick your poison, spreadsheet or your calculator. And you also need to be able to calculate this test statistic. And that you could use technology, but you still have to be able to program the correct equations. So let's get started. So this goodness fit test is a type of hypothesis test that determines the fit of a particular distribution. And so typically what we're doing here is qualitative data. And so what we're doing is categories, ideas. And you assign numbers to categories, but these are more category ideas. The book gave what was called a DICE example. And usually you don't do a DICE example because that's very theoretical for goodness fit tests. So what I am going to provide is a test example from another book that I used to teach out of that's more conducive to what an actual goodness fit test is. And so the idea is to compare something that's called an observed value, which is the experiment that you do, compare it to an expected value. And you'll be given that expected value depending on what type of idea that we're trying to prove. And typically they're uniform ideas. And when we get to the example, I'll explain that. But before we do that, I do need to introduce to you this idea of the test statistic. And it's defined by the observed values and expected values. And so what we're doing is kind of like a standard deviation style calculation a little bit, or a z-score calculation with a square in there. And so the observed value minus the expected value squared divided by the expected value. And then you take all these numbers and add them together. And that is our test score. And then we'll take these observed values and we'll set up a null hypothesis and an alternative hypothesis. Again, the degrees of freedom now will be the number of categories. And so again, it would be the number, not data points, but the number of categories now. And then the good fit test you'll see is almost all right-tailed, and that's what we're going to focus on. And the expected value for each cell needs to be at least 5 in order to do this test. And so obviously we're going to give you that, or performing the test would be semi-useless. So you'll see that when you end up being asked to perform the test, this will actually be true. And so to do this test, I decided to take the data. Again, this is from a different book, but this says employees want to know which days of the week employees are absent in a 5-day work week, employers, excuse me. And most employers, which would believe that it is absence is uniform, meaning that each day you should have the same amount of absence. And suppose that a random sample of 60 managers were asked which day of the week they had the highest number of employee absence. And then the results were distributed in this table. And the highest number of work absence occur with equal frequency during the 5-day work week. And here's our 5% significance level. So if you take a look at this, there is a process to walk through to calculate the test statistic. And so that's what we're going to do now. And here is the process. And so our degrees of freedom here is number of categories minus 1. And so we had 5 days of the week, and minus 1, which would be 4. We'll see that if you look up in the table, we have our chi-square table with degrees of freedom of 4 and a 5%, which is this one right here. Oops. And 5%, which would be this column right here. you see that our chi-squared statistic is 9.488. So now what we want to do is to compare that with our test statistic that we're actually going to calculate. So I think I skipped the beginning, sorry about that, but let's go up to the top again, where we have the null and alternative hypothesis, again with our alpha of 5%. And so we talked about the table part of it and got the chi-squared number. But what about our hypothesis? Well, here the absent days occur with equal frequency, and it will fit a uniform distribution. That'll be our null hypothesis. And then unequal will be our alternative hypothesis. And so what we're going to do next is walk through the calculation. So pause it for there a minute or so I could get up a table and walk you through this by hand. And so what I have here are the days of the week and the observed values, which is the number of absences per day. And if you add all this up, the total, again, was given to us is 60. And so what do we mean by this idea of uniform? Well, what we mean is that you have the same number of absence each day of the week. And so the idea is that you think about that being the mean, right? In the sense that we would have our expected value, you could think of that as well, right? So it'd be 60 divided by 5 days. And so that would be 12. So what we do here is to put 12 in each one of these. And so the next thing we want to do is to walk through the calculation of this test statistic. And so when we do that, I put up 3 columns. And the first one, oops, I forgot my squared here. The first one is the observed minus the expected. And so you could see here that this would be, say, 15 minus 12. So that would be 3. 12 minus 12. So that would be 0. 9 minus 12. And that would be minus 3. 9 minus 12 again is minus 3. And you could see this one is plus 3. So now we squared. 3 squared is 9, 0, my favorite number. And so you see everything turns positive and everything ends up being 9 except for the Tuesday where it is 0. So then the next step is you take the expected value and divide it into that number. And so this would be 9 divided by 12, and that would be 0.75. And here we'd have any number into 0 is still 0. And then you see these all end up being 9 divided by 12, which is 0.75. So the last step, you add this all up and you get 1.5 and 1.5. So our test statistic here is the number 3. So what I've done here is shown an Excel version of the table I just did on the whiteboard, and you could see all the different steps in the calculation. You could do one big calculation if you're good with generating formulas, but I think if you're definitely going to do it by hand, I think a nice 3-step approach is much more reliable and much less prone to make a arithmetic mistake. So if we go back to our calculation, you could see that I just calculated the test statistic, which is 3. And so here's the idea. Well, we got the chi-squared number from the table with the degrees of freedom and our 5% significance level. And since 3 is less than our 9.488, we want it to be greater than. We do not reject the null hypothesis, okay? And so if we don't reject the null hypothesis, that pretty much says that there's not significant evidence to conclude that the absence do not occur with equal frequency. So we don't know. Is basically what the test concludes. And so there is technology to help with this calculation to make it a little bit easier in the sense that you don't have to do the arithmetic. And so I will show you that in the next recorded lecture. What we'll do is this same problem using technology with the spreadsheet, and also show you how to use your calculator.